Everyone, myself Mr. P. Balakrishna, Assistant Professor, Department of ECE, Vignans, Nirila. Today, in this class, I am going to discuss about measurements of parameter. There are several parameters are there for the op amps. So, measurements of parameters. In this lecture, I am going to measure some of the parameter. So today I am going to measure the parameters are, first one is input offset voltage, which is nothing but VIOS, and the second one is input offset current, IIOS. Third one is input bias current, IBS, and the fourth one is PSRR, power supply rejection ratio, and the fifth one is CMRR, common mode rejection ratio. Last but not the least, sixth one is output offset voltage, which is nothing but VOOS. Coming to the first case is input offset voltage. First, before going to measure the parameter of input offset voltage, first I am going to tell you the definition of input offset voltage. What is input offset voltage? Here, when both the input terminals of an op amp is connected to ground, obviously we will get the output as 0. But instead of mismatching of the components present in the op amp, we may not get the output as 0. So rather than 0, we may get some amount of the output voltage, which is called as output offset voltage. To make that output offset voltage, we are going to apply some amount of the DC voltages at the input terminals of the op amp, which is nothing but input offset voltage. And in the formula wise, we are going to express input offset voltage is modulus of VDC1 minus VDC2. There is another formula and there is another way for the representing of input offset voltage. That is, to make our output offset voltage as 0, we are using the potentiometer at the input terminals of an op amp. By adjusting that potentiometer, we may apply the input offset voltage at the input terminals of an op amp to make the output offset voltage as 0. So, which is also treated as input offset voltage. Here, I am going to express input offset voltage with the help of potentiometer. For that, first, I am going to consider an op amp. Here I am considering an op amp. Here the op amp will consist of two input terminals. One is positive and the other one is negative. Generally, the positive terminal will be treated as non-inverting input terminal and the negative input terminal will be treated as inverting input terminal, and we are applying the supply voltages. Those are plus VCC as well as minus VEE, and we are having one output at the output side, which is nothing but output voltage V0. Now here I am going to consider 1 ohm and that will be connected to ground, and here I am applying another resistor 1 kilo ohm, and here I am connecting the potentiometer. Okay, the potentiometer is connected. So here I am connecting a resistance R1 and which will be connected to ground. Now this is open loop op amp. So by using this open loop op amp, so we want to calculate the input offset voltage, and here I am going to consider the node as A. So here we are applying the input at the inverting input terminal. So how can we calculate the input offset voltage? That will be applied at the input terminals of an op amp to make our output offset voltage as 0. So to calculate the potential at A, we are going to be used the voltage divider rule. So this will be taken as VE. So what happened is by using voltage divider rule, I am going to calculate VA. VA is equal to VE into 1 ohm divided by 1 kilo ohm plus 1 ohm. So we may get VE divided by 1000 plus 1. So 1 is very less value. So I am neglecting that 1. So finally we will get the potential at A node is VE divided by 1000. And this will be nothing but the input offset voltage. So to apply this input offset voltage at the input terminals of an op-amp to make your output offset voltage as 0. This is the way we are going to calculate the input offset voltage. Now we are using the same circuit for the calculation of PSRR. How can you calculate PSRR? And what is the definition of PSRR? First, PSRR is nothing but power supply rejection ratio, which is nothing but the ratio of input offset voltage divided by input offset voltage with respect to rate of change of one of the supply voltage while keeping other supply voltage as constant. So delta VIOS divided by delta VCC make VE as constant, which is also called as power supply sensitivity. Not only the power supply rejection ratio, which is also called as power supply sensitivity. Initially, we may adjust the supply voltages, dual supply voltage plus or minus 10 volts, and you can make output voltage as 0. Next, what I am going to do is, first step 1 is for this calculation of PSRR, step 1 is initially we make supply voltages are VCC and VE as 10 volts. Okay, now to make your output voltage V0 is equal to 0. Then what I am going to do is I am changing my VCC from 10 volts to 9 volts. Now VCC is equal to 9 volts. Now what happened is, because of this, the output voltage will be generated even though when both the input terminals are connected to ground. By adjusting that input offset voltage, okay, now we make the output voltage is equal to 0. So with the help of changing VCC from 10 to 9, we may calculate VIOS1. That will become some value for making your output voltage as output offset voltage as 0. Next, what I am going to do is once again I am changing my supply voltage from 9 to 10. Okay, now, and once again I am adjusting the output voltage as 0. Now what I am going to do is, now I am changing my supply voltage from 9 volts to from 11 volts. From 10 to 11 volts. Again I am going to calculate VIOS2, okay, second value VIOS2 to make my output offset voltage as 0. So from this, what we can conclude is PSRR will be equal to delta VIOS divided by delta VCC, make VE as constant. If you observe in this case, I doesn't change the value of VE, only I change the value of VCC. From 10 to 9 I changed, and then next from 9 to 11. There is a small correction in the last slide. Last time I told you that from 9 to 10, from there 10 to 11, but it's not possible like that. First you fix it from 10 to 9, from then 9 to 11. So what you will get is VIOS2 minus VIOS1 divided by VCC2 minus VCC1. So this is the way you are going to calculate the power supply rejection ratio. 0. Okay, so with the help of same circuit, we calculated two things. One is input offset voltage and the other one is PSRR. So next, I am going to calculate input offset current. So which is nothing but IOS. With that same circuit, we may calculate I bias. Okay, so first I am going to draw the input offset current, measurement of input offset current. So here I am using an op-amp. Okay, here it is positive terminal, negative terminal, and here I am connecting a resistance R. Across the resistance I am connecting a capacitor C1. Okay, and the resistance value R is equal to 7.2 mega ohm and C1 is equal to 0.01 microfarad. And at the inverting terminal also I am connecting a resistance in the feedback path. So R is equal to, here also I am considering 7.2 mega ohm, and across the resistance I am using a capacitor C, and here also it is taking as 0.01 microfarads. Okay, now this is the closed loop op-amp which is going to be used for the measurement of input offset current. First of all, we have to know about what is input offset current. When both the input terminals of an op-amp is connected to ground, we have to get the output voltage as 0. But because of the mismatches present at the input terminals of an op-amp, there will be some amount of input current is passing through the input terminals of an op-amp. So to make the output voltage as 0, we have to remove this input offset current also. So what is input offset current? Here I am representing IIOS is equal to modulus of IB1 minus IB2, and here I am going to consider the current passing through the inverting terminal is IB1 and the current passing through the non-inverting terminal will be taken as IB2, and here I am going to take the node as A and here I am going to take the node as B, and in this case I am going to take the node as C, and here I am going to take the node as D. Okay, now for the calculation of input offset current, first step 1 is short A and B. So if you short A and B, what happened? B is at potential 0. So if you short A and B, already we will get automatically we will get the potential at A is also equal to 0. According to the virtual ground concept, the potential at A will be equal to potential at C. So what happened? The C is also equal to 0. So now what I am going to do is I am going to assume the output voltage as V01. So V01 is equal to IB1 into R. Take it as equation number 1. Next, what I am going to do is I am going to short. Step 2 is I am going to short C and D. Short C and D. If you short C and D, what happened? The potential at D will be equal to V0. So the potential at C is also equal to V0. Here I am assuming the potential at D will be V02. So the potential at C is also equal to V02. Due to the virtual ground concept, the potential at A is also equal to V02. Now what happened is the current passing through the inverting terminal will be taken as V0 of 2 is equal to IB2 into R. So take it as equation number 2. From this we can easily write IB1 is equal to V01 divided by R and IB2 will be equal to V02 divided by R. Once we know the values of IB1 and IB2, then we can easily calculate the value of IOS, which is nothing but algebraic difference between the input currents applied at the input terminals of an op-amp. So in this way we are going to calculate the input offset current. So if you observe the circuit diagram, here I connected a capacitance C across the resistance R. Why I am connecting that capacitor C across the resistance R is, here I am considering the resistance R will be equal to 7.2 mega ohms, which is a very large value. To remove the noise in that resistance, or to remove the noise, or to bypass the noise in that resistance, we are going to connect the capacitors across the resistance. Now this is the way we are going to calculate the input offset current. Once we will calculate the input offset current by using the same circuit, we may calculate the input bias current also. What is input bias current? I bias. What is input bias? Which is nothing but the average of the input currents passing through the input terminals of an op-amp. So I bias is equal to IB1 plus IB2 divided by 2. Now what happened is, if you know the values of IB1 and IB2, so by using the same circuit we may calculate the values of IB1 and IB2. So just substitute the values in this equation, then we may easily get the value of I bias. So by using these two circuits, I calculated 4 parameters. What are I calculated 4 parameters. What are they is, first, with the help of first circuit, open loop op-amp, I calculated VIOS as well as PSRR, and with the help of second circuit, closed loop op-amp, I calculated the values of IIOS and I bias and the measurements of parameters. Okay, now coming to the measurements of parameters. Measurements of parameters. Today's class I am going to discuss about first one is CMRR and the second one is output offset voltage, VOOS. Okay, in the previous class I discussed about input offset voltage as well as input offset current, input bias current as well as PSRR. With these two things, the measurements of parameter topic is completed. Now I am going to explain CMRR. Okay, so for that I am going to consider an op-amp which is in the closed loop format. Here I am considering a resistor which is nothing but RF, and here I am considering a resistor which is nothing but R1, and here I am going to take a resistor is R1, and feedback resistance is considered here which is nothing but RF. Okay, in this case I am going to collect the output, so this is RF. So what I am going to tell you is, here I am going to calculate the CMRR. CMRR is nothing but the ability of the differential amplifier to reject the common mode signal is called as CMRR. So in the formula wise, how can we represent this CMRR is? So CMRR is expressed as, CMRR is equal to modulus of AD divided by AC. That is the ratio of differential voltage gain to the common mode voltage gain. So now I want to calculate CMRR value by using this closed loop op-amp circuit. In this case I am applying a common voltage Vs which is applied to both the input terminals of an op-amp. That's why I am calling it as a common common voltage Vs. So we all know that the output voltage of the differential amplifier is depends upon two factors. One is on differential voltage gain and the other one is on the common mode voltage gain. So whenever you express the output voltage, you may express the output voltage V0 is equal to AD into VD plus AC into VC. In this case, I am going to consider output voltage V0 is equal to AC into VC. Now, I am calculate the common mode gain first, which is nothing but AC. AC is equal to V0 divided by VC. What is VC? VC is nothing but the average of two input signals which we are applied at the two input terminals of an op-amp. So here what is the common signal? Vs. So both the input terminals the Vs voltage is applied. So what happened? So Vc is equal to Vs plus Vs divided by 2, which is nothing but 2 Vs by 2 we will get as Vs. So finally AC will be equal to V0 divided by Vs. So it is not enough for the calculation of CMRR, and we may require AD value also. Once we know the value of AD and AC, then we can easily calculate the value of CMRR. How can you calculate the AD value? By using this circuit here, which is nothing but the difference of input voltages. Here the potential at non-inverting terminal is VB and the potential at the inverting terminal is VA. When both the input terminals are applied at a time, then it is not possible to calculate output voltage. So what you want to do is you make one of the input terminal is connected to ground and calculate for the other and calculate the output by using the other input terminal. Take it as V01 and make other input terminal is connected to ground and another one will be enabled and calculate output voltage V02. Finally, the output voltage is equal to V01 plus V02. This is the way to calculate the output voltage. But what I am requiring is I want the difference of input voltages which we are applied at the two input terminals of an op-amp. So VD is equal to VB minus VA. For that, first what I am going to do is I am applying the input at the non-inverting terminal and the inverting terminal will be connected to ground. So what happened to this circuit? So this circuit will becomes an non-inverting op-amp. Why? Because I am enabling the input at the non-inverting terminal and I am making the inverting terminal will be connected to ground. So what happened for VB? So I am not concentrated on calculation of output voltage. I want to concentrate on the input voltages. So first I am going to calculate the value of VB by using voltage divider rule. We calculated VB as Vs into RF divided by R1 plus RF. Take it as equation number 1. Next, what I am going to do is now in this time I am making that non-inverting terminal is connected to ground and I am applying the input at the inverting terminal of an op-amp. Now at the node A, because of two inputs, the VA value will be generated. One is with respect to the VS and the other one is with respect to the feedback resistance. Okay now. So output voltage V0 also is used for the generation of VA. So first I am going to calculate by using non-inverting terminal is enabling and the output voltage is connected to ground. Just now only I told you if two inputs are acting at a time, then it is not possible to calculate that value. So we may calculate that value one after the other while making the other input terminal is connected to ground and finally club those two values, then we will get the output voltage. So first I am going to calculate VA1. VA1 is calculating while V0 is connected to ground. What happened when V0 is connected to ground? Now using voltage divider rule, VA1 is equal to Vs into Rf divided by R1 plus Rf. And next, this is when V0 is ground. And next, what I am going to do is, I am making Vs is connected to ground and V0 is enabling. So what happened for VA2? VA2 using voltage divider rule once again. V0 into R1 divided by R1 plus Rf when Vs is ground. So finally VA will be equal to VA1 plus VA2. So I want VD value. How can we calculate that VD? VD is equal to VB minus VA. What is VB? VB is nothing but Vs into Rf divided by R1 plus Rf. And what is VA? VA is nothing but VA1 plus VA2. So Vs into Rf divided by R1 plus Rf, and then plus V0 into R1 divided by R1 plus Rf. So these two terms are cancelled. We will get minus of V0 divided by R1 divided by R1 plus Rf. So what happened is we will get Vd is equal to minus V0 into R1 divided by R1 plus Rf. So what is AD? AD is nothing but V0 divided by Vd. So I am going to calculate V0 divided by Vd is equal to minus of 1 plus Rf divided by R1, which is nothing but the differential voltage gain AD. So already we calculated AC value and now we calculated AD value. CMRR is nothing but the ratio of differential voltage gain to the common mode voltage gain, which is nothing but AD by AC. Once we know the values of AD and AC, then we can easily calculate the CMRR value. This is the way we are going to calculate the CMRR value, that is measurement of CMRR value. Next, I am going to explain the last parameter, which is nothing but VOOS. Okay, VOOS is nothing but output offset voltage. That output offset voltage is generated because of input offset voltage as well as input offset current. Now first I am going to find out the effect of input offset current on output offset voltage. Later on I will calculate effect of input offset voltage on output offset voltage. First, I am going to calculate the effect of input offset current on VOOS. Okay, so what is VOOS? When both the input terminals of an op-amp is connected to ground, we have to get the output voltage should be 0. But instead of 0, if you are getting the value other than 0, which is nothing but output offset voltage. First I am explaining the effect of IIOS. For that, I am going to consider an op-amp plus, minus, and here I am going to consider it as RC, and here I am going to consider it as R1, and this one will be nothing but feedback resistance RF. Okay, so this is RF, and both the inputs are connected to ground, and here the current passing is I1 and here the current passing is I2. So now what we want to calculate is we want to calculate output offset voltage. Okay, so because of input offset voltage, input offset current, the output offset voltage is generated. When both the inputs are connected to ground, first we make one will be taken, and then next we will be take another input value. First I am going to consider the inverting terminal is active. Then what happened is we may calculate this total op-amp will be taken as inverting op-amp. So V naught is equal to minus RF by R1 into I1 into R1. Why? Because here it is connected to ground, but due to the mismatching, because of the input currents, there may be some input voltage is generated. So next I2 is the non-inverting is active and the inverting terminal is connected to ground. Now V02 is equal to, that circuit will becomes non-inverting op-amp. That will becomes 1 plus RF by R1 into I2 into RC. Now keep R1 is equal to RC, then what happened? R1 plus RF into I2. Okay, and V01 is equal to minus of RF by R1 into I1 into R1. Now the total output voltage, which is nothing but output offset voltage, is equal to V01 plus V02. Now what happened? R1 into I2 plus RF into I2 minus, here R1 cancel, we will get I1 into RF. Okay, I1 into RF. RF should be very much greater than R1. We will be neglect R1 into IB2. Finally, if you have taken RF as common, then you will get IB2 minus IB1. That IB2 minus IB1 is nothing but IIOS. So IIOS into RF. This is the effect of input offset voltage, input offset current on output offset voltage. Next, I am going to tell you about input offset voltage on VOOS. For that, I am going to consider an op-amp. So here it is plus and it will be connected to ground, and here I am going to take it as R1, and here I am taking a feedback resistance is RF, and it will be connected to V0. Now consider this one. Here you may not consider whether it may be the inverting input or whether it may be the inverting op-amp or whether it may be the non-inverting op-amp. You may choose any one of these two. Here I am considering it as a non-inverting op-amp. So the direction of the current will be like this. So the current passing through here, it is IF, and here it will be IA, and the potential at A is VA and the potential at B is VB. Now write down I is equal to VB minus 0 divided by R1, and IF is equal to V0 minus VB divided by RF. So here the input offset voltage is applied in between the input terminals. So here I am considering as VIOS is equal to VB is equal to VA. So what I am going to consider is according to VB is equal to VA is equal to VIOS, I am considering I is equal to VIOS divided by R1 and IF is equal to V0 minus VIOS divided by RF. Equate those two currents. So VIOS by R1 is equal to V0 minus VIOS divided by RF. So V0 is equal to VIOS common 1 by R1 plus 1 by RF. So you will get R1 plus RF divided by R1 into RF. This is about VIOS. So V0 is equal to, there we will get V0 is equal to R1 plus RF by R1 RF into VIOS. This is the effect of input offset voltage on output voltage. Output offset voltage. So finally V0 OS is equal to IIOS into RF plus VIOS into R1 plus RF divided by R1 into RF. With this, measurements of parameters of op-amp topic is completed.